Hello, welcome to the review of the new features and changes that Xilinx has made in our embedded software offering for the 2018.3 release. We'll start by covering some updates we've made to our PetaLinux build tools. Then, we'll cover some updates and new features we've added in our software stack. After that, we'll go into more detail about updates to some of the specific components of the software stack, and then wrap up by covering some new features available in the MicroBlaze soft processor. To start, we've made updates to our device tree generator tool to support video IP. Specifically, the device tree generator now properly configures the device tree for strings of IP and their properties to correctly support various processing pipelines. On the PetaLinux front, several key changes have been made to the underlying infrastructure of the tool. First, we have updated our supported host OSs to include Red Hat and CentOS version 7.5 as well as Ubuntu 16.04.4 LTS. While Vivado now supports Ubuntu 18.04 LTS, PetaLinux retains support for Ubuntu 16.04 in order to remain aligned with the underlying Yocto infrastructure. Next, we have made some changes with the Tickle engine that drives the PetaLinux tools. We have introduced a new version of XSCT called XSCT Trim, which is independent of both Vivado and XSDK. By using this version of XSCT, we have accomplished two goals. One, users can now install PetaLinux by itself without dependencies on other Xilinx tools. Two, the tools no longer have any dependency on the Eclipse GUI engine. This change allows PetaLinux to run properly in pure terminal environments, such as when connecting over a remote login. In addition, PetaLinux now has support for device tree overlay generation and FPGA manager. This support is useful for designs that need to either load PL logic bit streams after the main system is started or swap PL bit streams out at runtime. Finally, we have made some updates to the available PetaLinux BSPs. First, the ZCU 1275 board now has a PetaLinux BSP available that can be used to kickstart designs based on this board. In addition, the ZCU 111 board BSP has now reached production status and incorporates an SDFEC example design that includes both the needed soft IP drivers and example applications. Our embedded software stack has been updated in a number of ways. First, we have made updates to the Zynq UltraScale Plus MPSoC first stage bootloader to read SPD data from SODIMMs. This support is currently in an early access state and works on the ZCU 102 and ZCU 106 boards. In addition, we have published the first version of a dedicated user guide for the bootgen tool UG1283. This document not only covers all of the options required in the BIF files for use with the bootgen tool, but also covers the structure and layout of the boot image for Zynq 7000 and Zynq UltraScale Plus devices. Another major change we've made related to boot is support for ISSI flash devices. This support ranges from FSBL through U-Boot in Linux. Please see Answer Record 65463 on Xilinx.com for more details. The PMU firmware code for Zynq UltraScale Plus devices has been updated to support several key new features. First, the PMU firmware now supports hardware acceleration of SHA-3 authentication via the ZIL Secure library. This change will improve the performance of applications leveraging the SHA-3 hardware in Zynq UltraScale Plus MPSoC devices. In addition, PMU firmware now supports some new features that will make performing a warm restart easier. First, it now supports placing memories into DDR self-refresh mode when doing warm restart. This allows the system to reuse existing memory configurations when restarting rather than retraining the memory and losing data. We've also added support for idling peripherals located in the programmable logic during warm restart events. For more details on the use models and examples, please go to the Xilinx wiki at wiki.xilinx.com. Finally, our Linux kernel infrastructure has been updated with increased support for loading both full and partial bitstreams at runtime, as well as bitstream readback support. These improvements increase the flexibility of these systems by allowing designers to make sure that their system can adapt to workloads on the fly. Please see the Xilinx wiki for implementation details. Now we'll take a deeper dive into changes we've made in some specific software components of our software stack. For video processing, our stack now allows for headless EGL rendering pipelines without the need for an output to a display. This allows systems in high-performance compute or cloud applications to perform accelerated graphics handling without the need for running an X server. In addition, our stack has added support for Wayland and global buffer management. Support for reserved memory in the Direct Rendering Manager subsystem will now allow users to use a consistent memory space during the transition from initial system startup to the full Linux system. For VCU users, we've made a concerted effort to focus on quality and performance of the software. The details are highlighted in the table on the right, but it's important to call out that we now support HDMI and I2S audio as part of the software stack for robust multimedia video applications. In terms of OpenAMP, we have upgraded our stack to community version 2018.10, which was released in October at github.com/openamp. This update allows us to take advantage of a number of improvements made by the community to decouple components based on RP message and remote proc. In addition, the Xilinx OpenAMP user guide UG 1186 has been revised to provide more detailed examples and information related to debugging, including debug of remote applications loaded via the sysfs on Linux. Xen Hypervisor has also seen an upgrade to its latest community version, Xen 4.11. This update brings many community improvements, including increased reliability and better handling of interrupts within guests. In addition, Xen now supports cacheable shared memory between guests, including between Linux and bare metal guests. Finally, Xen now has options that can allow a system designer to reduce the size of the hypervisor to as few as 50,000 lines of code. A major change that directly affects software developers on Xilinx platforms without impacting code directly is a change we've made to the standard Xilinx license. As you can see highlighted in yellow, we have removed language that previously restricted the use of Xilinx generated code to running on Xilinx devices. By removing this language from the default license in our software, we have enabled software developers to more easily integrate Xilinx generated code into code bases that use more permissive licenses. Designers will primarily see this change in the licenses associated with Xilinx bare metal code, as well as our bootloaders and firmware. We'll wrap up today's discussion by covering some changes we've made to the MicroBlaze soft processor. Highlighted here are a number of updates and changes, but we're going to focus on memory access. Specifically, we've now added an option to the MicroBlaze configuration to support 64-bit memory addressing. While the core of the MicroBlaze ISA remains 32-bit, the processor can now access up to 18 exabytes of memory. This means that existing MicroBlaze code will continue to run unmodified while also opening the possibility to use more than 4 gigabytes of memory for memory-intensive applications. This capability is released as a beta feature in 2018.3 with full end-to-end support coming in a future release. In closing, we've covered a number of updates we've made that will directly improve the experience of Xilinx embedded systems designers. PetaLinux has switched to using XSET trim to allow it to be installed independently from Vivado and XSDK. Our multimedia stack has been made more robust, including bringing audio support into the mix. We've updated our default software license to work more natively with permissive software licenses. And finally, we've improved MicroBlaze to support native 64-bit memory addressing. For a full list of all changes present in the 2018.3 release, please take a look at UG 973. To download our tools such as Vivado, XSDK, or PetaLinux, please go to xilinx.com/download. For access to all of our open source collateral, including the Linux kernel, U-boot, and our bare metal software stack, please look on our GitHub page at github.com/Xilinx. For access to example designs and other technical resources, visit our wiki located at wiki.xilinx.com.